So we're going to be studying light, and this is pretty much how we view the universe. Astronomers use light to study the universe. Light is emitted by objects that are hot, like stars. Technology such as telescopes allow us to see and study more than we can see by our eyes standing on the Earth's surface. A good analogy is that it'd be the equivalent for us to look through our atmosphere into space is like looking at from a bottom of a swimming pool to see what's going on around or outside the pool. But by understanding the electromagnetic spectrum, we can determine what objects are made of based on the spectra we detect coming from the object. So let's study the light, and we can determine a lot of characteristics about the objects. And the Doppler effect is the apparent shift of light or sound, any wave, as it is in motion. So let's take a look at this cool picture here taken by the telescope that we'll be looking at here a little bit further. It's the one that's kind of the most famous here, and it's the Hubble telescope. And the Hubble telescope found this, and this is called Eagle Nebula. And the Eagle Nebula is an emission nebula. It's about 5.5 million years old, and it's about 6,500 light years from Earth. It is in the Milky Way galaxy. And the pillars are about 2 to 3 light years long, and the emission nebula spans about 20 light years. So it's tremendously large. But these are what we use. We use light. Here we have the Rosetta Nebula, a star-forming nursery, that there's tremendous numbers of stars, probably equivalent to numbers of sand grains that are located in here. And the colors provide a measure of how hot the various regions are. The temperatures range from the different colors from a few thousand degrees to 20,000 degrees to the blue regions. So the color is going to tell us something about the temperature ingredients. The Andromeda Galaxy, right, the nearest galaxy to our Milky Way, the nearest spiral galaxy. It's only 2 million light years away. And here's the Trifid Nebula. This is located in the southern sky, and you can view this during the summer. It's just got beautiful blues and kind of purples, even some oranges and pinks in there. So this is the study of spectroscopy. It's essentially studying light. Where spectroscopy is a very important tool for astronomy. Light is the energy that moves through space and can be thought of as either waves or particles. And the distance between the peaks of the light are called the light's wavelength. So light is made up of different wavelengths and frequencies. And we're going to be using a spectrometer in class. And these are instruments that help us break down these wavelengths. And we're going to be able to determine what the components of the objects that are emitting the light are made of. But light is very important. It's the key to studying the universe. And we use telescopes that allow us to get more and see more light. Where telescopes allow us to view tiny amounts of light from great distances. Light is a wave and carries information. Studying light, we study the characteristics of what produced it, example, stars. So if we're taking a look and studying light, we can actually determine a lot about that star. We can determine what it's made of. We can determine how far away it is. We can even determine its temperature. In the Hubble telescope, this is what views space from space with no atmospheric interference. So in other words, we go to space to actually view space better. So where does light come from? Well, it's either emitted or it's reflected. If it's emitted, it's given off as a result of an energy transfer or a transformation. But most of our world is based on reflected light. Light move in straight lines. We'll call these photons. They move in straight lines. These are called light rays. And they travel in bundles of energy called photons. Each photon has a specific quanta. It's a value, a quantity that it has to abide by. So if we have these fluorescent lights that reflect off of a textbook that we're reading or something in the room, it makes it to our eye. So we see most of our world from reflected light. So we're studying the electromagnetic spectrum. We're going back to it because the world in which we view is invisible light. Invisible light can be broken down. It can be broken down into the colors of Roy G. Biv, where we have red, orange, yellow, green, blue, and violet. But light travels at c, right, the speed of light in a vacuum of space. C is 186,282 miles per second. Yeah, it's pretty fast. The electromagnetic spectrum illustrates different forms of pure energy, where all of these objects are traveling at the speed of light, or c. So gamma rays have we'll just say a higher frequency. They have a higher frequency, they have more energy. And the higher frequency, the smaller the wavelength. Whereas the radio waves end has the same speed of light, but it has a larger frequency, it has a smaller frequency, it has a larger wavelength. So it has a long wavelength and a low frequency. So when we look at these pieces that are in here, radio waves, as we go from the lower energy side, right, lower frequency, lower energy, we go from radio waves to microwaves to infrared or heat To visible light, what we're familiar to UV light, this is typically what does damage to our skin. We think of ultraviolet light, that's why we put on sunscreen. To X-rays, to gamma rays. So all of these travel at sea, but they have different frequencies. So the greater the frequency, the greater the energy, the smaller the wavelength. Whereas the lower the frequency, the larger the wavelength. So lower frequency, lower energy. And if I break down visible light into the color components, we have red is located on the larger wavelength side of the spectrum. So this is a lower frequency. It has lower energy. Whereas the blue and the violet end have a higher frequency, a higher energy, and a smaller wavelength. So the lower the energy, the lower the frequency, the larger the wavelength. The higher the energy, the smaller the wavelength, the higher the frequency, right? Energy and frequency are related here. So you're going to want to watch this video. It just kind of shows, it's kind of short and sweet. We live in a world that's driven by light and light energy. And when we take a look at visible light, we're really looking at white light, and it can be broken down into the red, orange, yellow, green, blue, and violet colors. So what are photons? Well, photons are these packages. They're the bundles of energy that we view our world from. That we can view here that red light has a larger wavelength, and that we can actually quantify it as having a lower frequency than orange, than yellow, than green, than blue, and violet, where violet has the largest frequency. So when we look at white light and we separate it into its individual components, we would see that white light is composed of all the colors of the rainbow, Roy G. Biv, all together. And each of these have different characteristics. They have fundamental properties that make them different. That red is red. It cannot be separated into anything else. And orange is orange, and green, and blue, and violet. They all are, you cannot separate them any further. Now we'll do a little bit of work with this. We'll be studying the continuous spectra. This is called a thermal or a black body spectra. These are emitted by any object that radiates heat, right? Like our sun, that has a temperature. The light is spread out in a continuous band with every wavelength having some amount of radiation. For example, when sunlight is passed through a prism, its light is spread out into its colors, and that's what we call a Roy G. Biv. In the case of the picture above, it's actually Roy G. Biv backwards. So right here we have what's called an absorption spectra of hydrogen, and below we have what's called an emission spectrum of hydrogen. And we'll be studying these a little bit further in class. In real life, we don't actually always get what that perfect spectral lines look like. We get these blips, and these blips are emission and absorption lines. And we'll study this. I'm not going to read this now. We'll get a chance to do this in class. But I do want to end with the Doppler shift and the Doppler effect. The Doppler effect is what's called the apparent shift in frequency from a wave, right? It could be light or sound, from a source and the person that's receiving it. So let's say that there's a sound source. Let's say this is here. We can apply this to sound or light. But I think this analogy will make a little bit more sense to you. Let's say this is a sound source. As a car is traveling towards you, the wave fronts, right, the speed of sound is going to be constant. So the wave fronts bunch up. So a car traveling towards you is going to have a higher frequency traveling towards you. And then it's going to travel by you, and it's going to be having a lower frequency. So it's going to be like, and that's actually the sound. Actually, that was my best Doppler shift sound I've ever made in my life, I think. So, but don't worry, I won't ever do that again. And if it's moving towards us, we would say that it's shifted toward the blue end, a higher frequency end. And if it's moving away from us, we would say that it's moved toward the red shift. And that's really what the red and blue shift. So if we apply that to sound, we can also apply it to light. Stars emit light just like a light bulb. Stars and planets are in motion. So the Doppler effect shows the effect of an object that is in motion in two forms. The red shift if it's moving away, or the blue shift if it's moving towards. So if it's moving towards you, we say it's a blue shift. If it's at rest, this is what it'd look like. So let's look at this. Let's just use this line right here as a basis. If it was at rest, we would view it something that would be at this location. But if it's moving towards us, all of these color bands, or all of these absorption bands, would be shifted toward this end of the spectrum. And if it was moving away, they would all be shifted, right? Moving away, it tells us that it's a red shift. All of these would just be shifted toward this end of the spectra. And that's what we're finding out about the cosmos, that objects, galaxies, are moving away. They're all moving away from us, and that tells us that they're shifted to the red. So we can study these shifts and learn about the cosmos itself, all through light.